In older homes where there is no existing grounding, the National Electrical Code, referred to as NEC, allows for alternative grounding methods in certain situations. One of these methods is the grandfather clause. The grandfather clause states that electrical installations that were in compliance with the NEC at the time of their installation are not required to be upgraded to current code requirements unless renovations or additions are made. Brown fault circuit interrupters, referred to as GFCIs, are essential for providing safety and protection from electrical shock, especially in areas like kitchens and bathrooms. While current code requires GFCI protection in these areas, the grandfather clause may allow for an exception. An inspector may question the grounding method because, firstly, GFCIs typically require a grounding conductor to operate correctly, and secondly, older homes without existing grounds may not have a proper grounding system. To explain the grandfather clause to an inspector, you can firstly point out that the electrical installation was compliant with the NEC when it was installed. Secondly, explain that the GFCIs are class A GFCIs, which do not require a grounding conductor to operate, and thirdly, provide documentation from the manufacturer of the GFCIs confirming their suitability for use in ungrounded locations. If the inspector is not satisfied with the grandfather clause, other alternative grounding options include, firstly, installing a grounding rod and wire, secondly, bonding the electrical system to a water pipe or other grounded metal object, and thirdly, using a non-metallic sheath cable with an equipment grounding conductor. The grandfather clause only applies to existing installations. New circuits or renovations must meet current code requirements. It is essential to ensure that the GFCIs are installed correctly and tested regularly to ensure their effectiveness. An inspector may have further questions or concerns, so it is important to be prepared to provide clear and accurate information. GFCI receptacles are designed to protect people from electrical shock. They constantly monitor the current flowing in a circuit. If there is an imbalance, indicating current leakage, the GFCI trips and cuts off the power very quickly. This happens in a fraction of a second, preventing dangerous electrical shocks. In a typical 120 volts electrical system, the GFCI is designed to trip when it detects a leakage of current as low as 5 milliamps. This sensitivity is crucial for human safety. Thus, the GFCIs are designed to trip when a ground fault exceeds 6 milliamps. These GFCIs are typically used in residential settings. Other types of GFCIs with different tripping thresholds are used in industrial or commercial applications. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. Proper wiring is essential for the GFCI to function correctly. It's also important to test the GFCI after installation using the test and reset buttons on the device. Regular testing of GFCIs is recommended to ensure they are functioning properly. You can test them monthly to ensure that they are working. When a GFCI trips, it indicates that there is a ground fault. It is important to identify and correct the cause of the ground fault before resetting the GFCI. Common causes of ground faults include damaged wiring, wet conditions, and faulty appliances. If you are unable to identify or correct the cause of a ground fault, it is recommended to consult a qualified electrician. GFCI receptacles are available in various configurations, including standard receptacles, circuit breaker replacements, and portable units. The choice of GFCI depends on the specific application and the level of protection required. In kitchens, GFCIs are typically required for receptacles serving countertop areas. This is to protect against electrical shock hazards associated with water and appliances. In bathrooms, GFCIs are required for all receptacles. This is due to the increased risk of electrical shock in wet environments. Outdoors, GFCIs are required for receptacles that are readily accessible. This is to protect against electrical shock hazards associated with wet conditions and outdoor equipment. When replacing a standard receptacle with a GFCI, it is important to ensure that the wiring is compatible. In some cases, additional wiring or modifications may be required. It is also important to label the GFCI receptacle to indicate that it provides GFCI protection. This helps to inform users of the safety features of the receptacle. GFCIs do not protect against overloads or short circuits. They only protect against ground faults. For overload and short-circuit protection, circuit breakers or fuses are required. It is important to understand the difference between GFCIs and circuit breakers. GFCIs protect against electrical shock, while circuit breakers protect against overloads and short circuits. Both GFCIs and circuit breakers are essential components of a safe electrical system. When working with electrical wiring, it is important to take precautions to prevent electrical shock. Always turn off the power at the circuit breaker before working on any electrical components. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electrical wiring, it is recommended to consult a qualified electrician. The NEC is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect changes in technology and safety practices. It is important to stay up to date on the latest NEC requirements. State and local codes may also have additional requirements for electrical installations. It is important to check with your local authorities to ensure that you are in compliance with all applicable codes. Electrical inspections are conducted to ensure that electrical installations meet code requirements. Inspectors may identify deficiencies that need to be corrected. It is important to address any deficiencies identified by an inspector in a timely manner. Ignoring electrical code requirements can lead to serious safety hazards. It is important to prioritize electrical safety in all electrical installations. Grounding is an essential part of electrical safety. It provides a path for fault current to flow back to the source, allowing the circuit breaker to trip and de-energize the circuit. In older homes without grounding, alternative grounding methods may be permitted by the NEC. However, it is important to ensure that these alternative methods provide adequate safety. One common alternative grounding method is to use a GFCI receptacle. GFCI receptacles do not require a grounding conductor to function properly. However, they provide a high level of protection against electrical shock. Another alternative grounding method is to install a grounding rod and wire. This provides a direct connection to ground. However, it is important to ensure that the grounding rod is properly installed and that the grounding wire is properly connected. Bonding is another important aspect of electrical safety. It involves connecting all metal parts of the electrical system together to create a common ground. This helps to prevent voltage differences between metal parts, which can cause electrical shock. In older homes, bonding may not be as extensive as it is in newer homes. However, it is important to ensure that all metal parts are properly bonded. Surge protection is another important aspect of electrical safety. It protects against voltage surges caused by lightning or other sources. Surge protectors can be installed at the service entrance or at individual receptacles. It is important to choose surge protectors that are rated for the voltage and current of the electrical system. Arc fault circuit interrupters, referred to as FSIs, are another type of circuit breaker that provides additional protection against electrical fires. FSIs detect arc faults, which are a common cause of electrical fires. They trip and energize the circuit when an arc fault is detected. FSIs are typically required in bedrooms and other areas where there is a high risk of electrical fires. Electrical safety is an ongoing process. It is important to regularly inspect your electrical system and address any potential hazards. If you are not comfortable working with electrical wiring, it is recommended to consult a qualified electrician. The electrical system is a complex system, and it is important to understand how it works. By taking the time to learn about electrical safety, you can help to protect yourself and your family from electrical hazards. In the specific case of an old home with no existing grounds, the following steps should be considered. Firstly, assess the existing wiring. Determine the type and condition of the wiring. Look for any signs of damage or deterioration. Secondly, determine the grounding options. Consider the alternative grounding methods permitted by the NEC, such as GFCI protection or installing a grounding rod and wire. Thirdly, consult with an electrical inspector. Discuss the grounding options with the electrical inspector and obtain their approval. Fourthly, install GFCI protection. Install GFCI receptacles in all areas where they are required by code, such as kitchens, bathrooms, and outdoor areas. Fifthly, consider whole house surge protection. Install a surge protector at the service entrance to protect against voltage surges. Sixthly, educate occupants about electrical safety. Inform the occupants of the home about electrical safety practices, such as testing GFCIs regularly and avoiding overloading circuits. By following these steps, you can help to ensure the safety of the electrical system in an old home with no existing grounds. Remember that electrical work can be dangerous, so it's always best to consult with a qualified electrician if you are not comfortable performing the work yourself. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for specific electrical needs and code requirements. Ensure the selection of appropriate wire gauges for branch circuits and main feeders, referencing NEC Table 310.15 for ampacity based on conductor type and insulation temperature rating. Proper sizing prevents overheating and potential fire hazards. Be mindful of voltage drop, especially in long circuit runs. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use a larger conductor size to minimize voltage drop and ensure proper equipment operation. Consider rating factors for conductors in conduit or cable assemblies with multiple current carrying conductors. Adjust ampacity based on the number of conductors and ambient temperature as per NEC tables. Use appropriate overcurrent protection, such as circuit breakers or fuses, sized according to the conductor ampacity and equipment requirements. Avoid oversizing overcurrent protection, which can lead to conductor damage in overload conditions. Properly torque all electrical connections to specified values using a calibrated torque wrench. Loose connections can cause overheating, arcing, and potential fire hazards. Identify and label all circuits clearly at the panel board and at each outlet or device. Proper labeling facilitates troubleshooting and maintenance. Use appropriate wiring methods for the environment, such as non-metallic sheath cable, conduit, or cable tray. Select wiring methods that are suitable for the location's environmental conditions, including moisture, temperature, and corrosive substances. Ensure proper support and securement of all wiring and equipment. Use appropriate fasteners and supports to prevent strain on conductors and connections. Maintain proper working clearances around electrical equipment, such as panel boards and transformers. Provide adequate space for access and maintenance as required by the NEC. Use ground fault circuit interrupters, referred to as GFCIs, in areas where electrical equipment may come into contact with water, such as bathrooms, kitchens, and outdoor locations. GFCIs protect against electrical shock by detecting ground faults and interrupting the circuit. Use arc fault circuit interrupters, referred to as ASIs, to protect against electrical fires caused by arcing faults. ASIs detect arcing conditions and interrupt the circuit to prevent fires. Consider using surge protector devices, referred to as SPD, to protect sensitive electronic equipment from voltage surges. SPD diverts surge current away from equipment to prevent damage. Inspect and test electrical equipment regularly for signs of wear, damage, or malfunction. Schedule periodic inspections and maintenance to ensure the continued safe operation of the electrical system. Follow all applicable electrical codes and standards, including the NEC and local regulations. Stay up to date on the latest code requirements to ensure compliance. Obtain necessary permits and inspections for electrical work. Comply with all permit requirements and schedule inspections to verify code compliance. Hire qualified and licensed electricians for electrical work. Ensure that electrical work is performed by competent professionals who are knowledgeable about electrical codes and safety practices. Provide training to employees on electrical safety procedures. Educate employees about the hazards of electricity and how to work safely around electrical equipment. Use lockout/tagout procedures to de-energize electrical equipment before performing maintenance or repairs. Prevent accidental energization of equipment during maintenance. Wear appropriate personal protective equipment, referred to as PPE, when working with electrical equipment, including safety glasses, gloves, and footwear. Protect against electrical shock, burns, and other hazards. Avoid working on live electrical circuits whenever possible. De-energize circuits before performing any work unless it is absolutely necessary to work on a live circuit. Use extreme caution when working on live electrical circuits. Follow all safety procedures and use appropriate PPE to minimize the risk of electrical shock. Never overload electrical circuits. Avoid plugging too many devices into a single circuit, which can cause overheating and potential fire hazards. Use power strips with surge protection to provide additional outlets and protect against voltage surges. Avoid running extension cords across walkways or under rugs, where they can be damaged or create tripping hazards. Inspect extension cords regularly for signs of wear or damage and replace them if necessary. Keep electrical equipment and wiring dry. Avoid exposing electrical equipment to water or moisture, which can create electrical shock hazards. Use ground fault circuit interrupters, referred to as GFCIs, in areas where electrical equipment may come into contact with water. Follow manufacturer's instructions for the safe use of electrical equipment. Read and understand the operating instructions before using any electrical equipment. Unplug electrical appliances when not in use. Save energy and prevent potential hazards by unplugging appliances when they are not being used. Teach children about electrical safety. Educate children about the dangers of electricity and how to avoid electrical shock. Post emergency contact information near the electrical panel. Make sure that emergency contact information is readily available in case of an electrical emergency. Have a fire extinguisher readily available in case of an electrical fire. Know how to use the fire extinguisher properly and keep it in a readily accessible location. If you experience an electrical shock, seek medical attention immediately. Electrical shock can cause serious injuries, even if you feel fine afterwards. Report any electrical hazards to the appropriate authorities. Help prevent accidents by reporting any electrical hazards that you observe. Remember that electrical safety is everyone's responsibility. By following these guidelines, you can help to create a safer electrical environment for yourself, your family, and your community. When addressing the absence of grounding in older homes, it is crucial to prioritize safety and adhere to the NEC guidelines while considering the existing conditions. Although the grandfather clause may offer some leniency, it is not a blanket exemption from all safety requirements. A thorough evaluation of the electrical system is essential to determine the most appropriate course of action. One approach is to install GFCI protection on all ungrounded outlets. GFCI receptacles do not require a grounding conductor to function and provide a high level of protection against electrical shock. However, it is important to label these outlets as GFCI protected, no equipment ground, to inform users that there is no grounding conductor present. Another option is to install a grounding conductor to all outlets. This can be a challenging task, especially in older homes with limited access to wiring. However, it is the most effective way to ensure a safe and reliable electrical system. If installing a grounding conductor is not feasible, consider using a combination of GFCI protection and surge protection. GFCI protection will protect against electrical shock, while surge protection will protect against voltage surges. It is important to note that surge protection alone is not a substitute for grounding. Surge protectors divert surge current to ground, so they will not function properly without a grounding conductor. When working with older wiring, it is essential to inspect it carefully for signs of damage or deterioration. Old wiring can become brittle and cracked, which can create electrical hazards. If the wiring is in poor condition, it should be replaced. It is also important to ensure that the wiring is properly sized for the load it is carrying. Overloaded wiring can overheat and cause a fire. Consider upgrading the electrical panel to provide more capacity and improve safety. Older electrical panels may not have enough capacity to handle the demands of modern appliances and electronics. A new electrical panel will also provide better overcurrent protection and ground fault protection. Consult with a qualified electrician to determine the best course of action for your specific situation. An electrician can assess the existing electrical system, recommend appropriate solutions, and perform the necessary work to ensure a safe and reliable electrical system. When explaining the situation to the electrical inspector, be prepared to provide documentation and explanations to support your approach. Clearly explain the existing conditions, the proposed solutions, and the safety measures that will be implemented. Be respectful and professional in your interactions with the inspector. Remember that the inspector's job is to ensure that the electrical system is safe and complies with code requirements. By working cooperatively with the inspector, you can help to ensure a positive outcome.